This is the circuit for the differential input amplifier based on a long-tailed pair. This is the pair, this is the long tail. The values of the resistors and the capacitors shown are not correct. You'll have to fix those yourself. However, there are a couple of things I wanted to show you about simulating with this circuit. As it's set up at the moment, it produces a common mode input. That is, the same signal is put into V1 and V2 because both of these voltage sources, V in 1 and V in 2, are set to produce an AC waveform with a magnitude of 1 and a phase of 0. If I wanted to put in a differential signal, then there's two ways to do it. I could either change the magnitude to -1, or I could change the phase to 180 degrees. Probably easier to change the magnitude to -1. However, if that's all I did, then I'm actually putting in a differential signal with a magnitude of 2. Because when this V in 1 produces an output of 1, this V in 2 is producing an output of -1, which makes the difference, V1 minus V2, equal to 1 minus -1, or 2. If I wanted to produce a differential input voltage of unit magnitude, I'd need to set this one to a magnitude of 0.5 and this one to a magnitude of -0.5. Then run the simulator, place a curve, and we'll take dB of V out divided by V1 minus V2. So that's the ratio of the output to the difference between the two input signals, which is the differential input, and I get a graph that looks like this. These particular values, it's almost constant at around 43 dBs. To work out the input impedance in the differential mode case is fairly straightforward. Just make sure that this is set to AC 0.5 and this is set to AC either minus 0.5 or 0.5 with the phase offset of 180 degrees, and do your simulation. Probe then you want the differential input, which is V1 minus V2, divided by the current flowing into the circuit. Now, the current into the circuit is either the current through C1 or the current through C2. You only need one of them, because for a differential mode, the current through C1 here is going to be the same as the current coming out through C2 there. So C1 hash N or P, doesn't matter, gives me a graph of the input impedance, and it's coming out to be around about 8.4, 8.5K or so in this example. The input impedance for a common mode signal needs the inputs set back to the common mode settings, and then do another run. Now, again, what you might think is the answer would be V1, which is the same as V2, divided by the total current flowing into the circuit, which is the current through C1 plus the current through C2. But if you type C1 hash N plus C2 hash N in this circuit, you will end up with this. 5 teraohms, well actually 4.8 teraohms. Is that right? No, it's not. While Simetrix is quite good at deciding that impedances must be positive, therefore not worrying about whether you type hash N or hash P for the current through a capacitor, if you add up two currents through two capacitors, then it's a bit more important to get it right. I added C1 hash N, which is the current flowing this way, to C2 hash N, which is the current flowing that way. Now, that current is almost exactly equal and opposite to the current flowing this way. It's the current flowing this way, which is the same as the current flowing that way. bit confusing. Think about it for a while if you're not sure. The way to get round this and plot what you really want is V1 divided by C1 hash N plus C2 hash P. And now it's the common mode voltage going in divided by the sum of the current flowing that way through C1 in the N direction and that way through C2 in the P direction. And that gives me about 5 kilo ohms, which is much more reasonable and much closer to what I'm expecting. It's just something that you need to watch out for.